Good morning, everybody. My name is 𝗀𝗶𝗇𝘁, and today I have the chance to introduce the speaker of this first talk of the new season for Thermal Transport Café. It's with great pleasure that I introduce Bladimir Ramos Alvarado, who is assistant professor at Penn State and former graduate from Georgia Tech. I had personally the pleasure to work with Bladimir in a special issue for liquid-cooled heat sink in applied thermal engineering. And so it's with great pleasure that today I introduce him. Bladimir, thank you very much for accepting our invitation to give this talk, and I'll hand it over to you for now, and you can get started whenever you want.
All right, Matteo, thanks so much for the introduction, and thanks so much for inviting me to this wonderful event. As I was saying, I'm gonna turn off my video for now to save on bandwidth because I'm getting some messages of unstable internet connection, so maybe that will help our presentation to go smooth. All right, so I think that's gonna save on, and yeah, let's get started. Okay, so today what I'm going to talk about, and to fulfill the objectives of this Thermal Transport Café, I'm going to show you some of my findings, but also some of the challenges, the issues, aspects where I need feedback, aspects where I want to create discussion on nanoscale interfacial conductance and thin film evaporation. And I'm going to discuss specifically the issues with interfacial modeling, polarization wettability, and interfacial entropy. A brief outline of my presentation is going to be like this. First, we're going to talk about my motivation to study heat transfer across solid liquid interfaces, the governing mechanisms of interfacial heat transfer as we understand them, molecular dynamics modeling of solid liquid interfaces, where I want to put emphasis on the challenges and opportunities that we have to do research, theory and simulation of weighting properties as a metric to model interfacial affinity. And then I'm going to talk about a case study, alumina-water interfaces, interfacial thermal transfer and wettability, interfacial heat transfer, and now alumina-water interfaces. And lastly, some questions for open discussion. As you can see, there's no conclusions, but you know, I would like to open this communication in two ways, right? So my main motivation to study heat transfer across solid liquid interfaces is photothermal therapy with novel metal nanoparticles, in which we can have, let me activate my laser pointer. Oh, fantastic. Photothermal ablation and drug delivery system, which both are enabled by near infrared light radiation on particles as plasmonic particles that are going to create that change in the temperature of the particle, and those temperature-induced changes are going to create breakage of the chemical links that carry the drugs, or thermal ablation. Those two objectives are going to be enabled through solid liquid heat transfer. The main mechanism here is the main modulation of temperature here is the amount of heat that goes from the solid into the liquid, driven by the main mechanism that I am targeting, interfacial chemistry, the complex interplay between temperature, linkage, the breakage of the links, and temperature, heat transfer, and chemistry. Those are the three elements that we want to account for. And as in my theoretical findings have been shown, interfacial liquid structuring is super important for solid liquid heat transfer. Again, this is for applications in the treatment of cancer, but also can be applied to imaging, right? Another applications that I'm interested in with regards to solid liquid interfaces is nanocomposites for heat transfer applications, colloidal nanoparticles as in nanofluids, and particularly for this presentation, filtration and desalination in porous alumina membranes, where obviously the alumina-water interface is fundamental. And lastly, you know, desalination applications and filtration in using nanoscale systems. All right. To begin this discussion, I would like to briefly go over the governing mechanisms of interfacial heat transfer as we understand them. right? So over many years that we have studied this, we have a good knowledge of the main parameters that govern interfacial heat transfer. Interfacial bonding, right? The strength of the bond between atoms of across the interface are going to determine the effectiveness of heat transfer, but also the modal mismatch that you see on both sides of the interface. The better the match between modes, the better the energy transfer. Roughness, even at the nanoscale, even in my simulations at the atomic scale, roughness plays a big role in the amount of energy that is being transferred across interfaces, and particularly for solid liquid interfaces, liquid structuring at the interface. What does that mean? The bias that the solid imposes on the liquid at the interface. You don't have that issue with solid-solid interfaces because solid atoms are not that mobile. But when it comes to solid liquid interfaces and the molecules of the liquid being the energy carriers, that becomes a big issue for heat transfer, one of the governing parameters here. Some recent findings have shown that the interplay between these four is quite complex. For example, let me show you this example by 𝗃𝗃, where here what we can see is the interfacial conductance, right, of a solid liquid interface increasing as a function of the contact angle, right? So the contact angle is increasing. That means the solid becomes more hydrophobic. In theory, that says that the solid liquid interface doesn't have a strong affinity, but the thermal boundary conductance increases regardless, right? And here we see a graph, a set of data points showing that the contact angle actually increases for different systems, from bare gold to other interfaces, chemically modified. Okay, so the explanation here is that this parameter played a major role in heat transfer. The energy bonding across the interface was not that strong, but the modal mismatch was almost perfect. Why? They were using hydrocarbons, liquids, and hydrocarbons to create that match between gold and a hydrocarbon. So they were effectively decreasing that mismatch at the interface. Then, okay, so you're saying that this is a good example. I'm saying, right, this is a good example of mod overlaps into the heat transfer. But then, if we look at this other work, there was a perfect, mostly perfect overlap as a function of temperature for a similar kind of system, and there was no correlation whatsoever observed in the conductance. What these authors eventually observed is that a multiple complex set of interactions were conducive to explain what was going on, and the parameter that they used was the structuring at the solid liquid interface. All right. So in order to investigate this in a sound, physically sound way, we need to use a modeling approach that can capture most of the physics, the chemistry, and the structuring of the interface. But first, let me discuss some of the problems, the limitations, and the opportunities for doing this with molecular dynamic simulations. This is how we usually model solid liquid interfaces, right? A very simple Lennard-Jones potential that has two parameters, epsilon and sigma, right? These are parameters that need to be determined, while R is the distance between atoms at the interface, only accounts for van der Waals forces, and sometimes we include electrostatic forces. How do we do that? By calibrating epsilon and sigma such that both are included in our model. All right, but then how do we actually do that? First, this is the first option. This is a widespread empirical process that is called either Mathiesian or Vetter-Lott mixing rules, in which the sigma parameter is determined by the arithmetic mean of these two parameters, and the epsilon parameter, the energy parameter of the interaction, is calculated by the geometric mean. No physically sound basis for doing this, and the inappropriateness of this method has been demonstrated in a paper from, I think it was from the 80s, and where it was clear that this method is valid for atomic non-reactive gases, and what we have in these solid liquid interfaces is not even close to a monatomic non-reactive gas system. And you can go over the literature and we can find this method applied in many different papers. Sometimes we are eager, right, to show that our model has some level of prediction of experiments, and we neglect the importance of properly modeling the interface. Okay, second method that has been used in the literature, microscale matching of macroscopic wetting behavior. What we do here is that we go to the literature or we conduct experiments, we measure the contact angle on a surface, and we try to match that in size-independent molecular dynamic simulation. That's, in theory, that's impossible to do. Molecular dynamic simulations are size-dependent. What we do is an extrapolation to the thermodynamic limit in which we can retrieve that macroscopic calculation. The process is more physically sound than the first one. However, the issue is that we need to calibrate one parameter while we keep the other one constant. And still, sometimes they rely on this calculation, and this calculation would give you the equilibrium distance between the solid atoms and the liquid molecules. And oftentimes that calculation is not very physically sound. When you try to compare that to AFM calculations or DFT calculations, electronic structure method calculations, you see that the equilibrium distance between the solid and the liquid is not really what is predicted from this equation. Again, it's not physically sound. And even if that's possible, we would have an infinite number of possibilities for obtaining that desired contact angle. If we are having two parameters and we are keeping one constant, we need to close the problem with another variable, okay? And lastly, we have curve fitting of DFT-derived absorption curves. What we do here is that we create a system, super small, in which one monomer of the liquid of interest interacts with a tiny model of the solid, and the absorption curve is calculated. Then, using this force field, we try to obtain the parameters. However, DFT calculations have a poor description of van der Waals forces. And again, if we only have one curve, and these calculations are also orientation dependent, based on the orientation of the molecule with respect to the solid, we're going to get different absorption curves, and we only have two parameters to fit. So again, the issues. But these are issues, but also opportunities. New electronic structure calculations, such as random phase approximation in quantum Monte Carlo, present a good and physically sound alternative with a high accuracy to calculate non-bonded interactions. Also, if we were to perform interface structure probing experimentally and surface chemistry characterization through computations and experiments, we could build more physically sound interface models. And lastly, reactive force fields such as REACTs and some others have been neglected for studying heat transfer. So yeah, that's why I wanted to focus some time on this slide so we can go back to the discussion on how to improve our modeling. All right. Then this part, these slides on are going to talk about some of the calculations that I do in my group to model heat transfer and interfacial affinity. First, we calculate interfacial affinity. We characterize interfacial affinity through wettability simulations at the nanoscale, which, as I explained, they can be expanded to the thermodynamic limit by performing extrapolation. We essentially allow, in this case, a group of water molecules to equilibrate on a solid, given a set of interactions that later on I'm going to discuss how the extensive work that we do to characterize them. The result could be that we either have hydrophobic conditions or hydrophilic conditions, and these depend on the quality of the interface model. We calculate the work of adhesion for every interface as the change of the free energy of the system given by the energy change in the interaction energy between solid and liquid molecules. The entropy change, which is not here the thermodynamic property, but it's a characterization of the change in the state of order from the bulk, where it's highly disordered, to the interface where we have the bias imposed by the solid. Okay, And that's also equal, as we know from thermodynamics, to the surface tension times 1 plus the cosine of the contact angle. We have created a model. So, okay, so this calculation is kind of easy, part of them. The contact angle can be obtained from my simulations. The surface tension can be obtained also from the simulations. This energy calculation is a very straightforward calculation of the summation of all the energy interacting in the system. But this one is tricky. This one's very tricky, and no theoretical model has been fully successful at predicting it. We have come with a kind of engineering approach to answering this question, in which we calculate the work of adhesion as a total energy of interaction calculation, which is what I'm representing here, in which we use the energy of interaction between one single molecule in an infinitely large surface of solid atoms. And then we calculate that energy as given here, right? Energy per unit atom. Then we integrate that energy per atom or per molecule that we have over the distribution of liquid particles that we model as a Boltzmann distribution. In the Boltzmann distribution, we include this tiny fitting parameter that eventually helps us to account for interfacial entropy change. That fitting parameter, even though it seems that it's a fudge factor that we are including there, the physics built in within this model are that strong that having one data point is enough to calibrate the full spectrum of wettability in our models. Then let me show you a case study of the application of these methods for alumina-water, in which we model the liquid solid interfaces through van der Waals forces and also electrostatic forces in a separate manner. They were not put together into a single potential, but they were split into two. And for that, we started with the clay force field that has been developed for ceramics interacting with water for many years. But we encountered some interesting issues. For example, in this paper in 2011, they tried to obtain wettability, try to model wettability with this force field. However, look at the shape of this droplet. Even if it's tiny, there is no physically sound shape here. And looking from above, it looks kind of weird, right? We had to reparameterize the partial charges in the system because we observed that they were off the charts. They were completely out of the physical range, and we obtained now a physically sound droplet shape. Check this other illustration that we have presented from our implementation of the clay force field as presented originally. As you can see, the water molecules align with the surface, indicating that there's likely a rather enhanced electrostatic force as compared to the reparameterization that we did. And that's exactly what happened. When we probe the electric field at this distance from the interface, we observed that we had an over-exaggeration of the electric field of the interface was way over the charts. That's why the molecules were arranged in this shape. They were polarized. They were effectively polarized. And we reparameterized the electrostatic force field using reactive force field simulations. In these reactive force field simulations, not only the interactions of the van der Waals forces are recalculated at every time step, but also the electrostatic force field, the electrostatic forces are recalculated and equilibrated. All right, so that's the aspect of the interface interactions. But what about the chemistry? Okay, so usually when you model a solid liquid interface in molecular dynamic simulations, what you do is you cleave a solid surface, creating a set of atoms, interface atoms that are chemically active. Their oxidation state, their valence state is not completed, so we need to passivate them, and we passivate this interface based on what we observed in the literature, and we did it with hydroxyls. And in this case, we are presenting here two different cases in which the hydroxylation was not complete, this side of the model, and this one where the hydroxylation was complete. The first case has some oxygen atoms that are not fully passivated. And even though we made efforts here to create a more realistic interface, as you can see, the results are not too, the geometry of the droplet is not that physically sound. And when we fully passivated the interface, you see, now we follow the profile that we were expecting to observe. This again highlights, one, the importance of how you model the solid-liquid interactions, as in van der Waals forces, electrostatic forces, but also the chemistry of the interface, how you properly passivate an interface exposed to a liquid. As you can see here, we did a lot of work, right, just to get the interface model right. Lots of work. And after this, well, we can perform more calculations. Now that we know that our interface model is physically sound, now we can study wettability. In this case, we consider 3 different surfaces: the 0001 plane of alumina, the 1210 plane of alumina, and amorphous alumina. We don't know which plane is going to be in contact with water, so it's good that we have this characterization for different planes. And as you can see, we observe an isotropy of wettability, which has been reported before, and it's also predicted and explained by our wettability model, and more recently by experiments. And where is the effect of the atomic planar density? Right here in this energy per unit molecule. So now that we have this fully characterized interface, the wettability conditions are characterized, we were able to solve for the entropy change of the interface as indicated in this equation. How? Well, we have the contact angle. We know the surface tension of the water model that we are using. This calculation is quite straightforward. And then we can solve for the entropy change. Okay, and this is how we did it right here. As you can see, if we could get some, just to interesting observation here, that the hydrophobic surface had less interfacial entropy, and the hydrophilic one had a higher level of interfacial entropy. All right, and with that, we finished our characterization of interfacial affinity and interfacial modeling, and then we were able to move on to interfacial heat transfer. Okay, so some traditional measurements of TDTR, of the thermal boundary conductance, have shown that, well, this is kind of a old work, 2009. In this work by, I think it was 𝗀𝗃𝗃, who published this experimental results. And as you can see, there's some sort of a relationship between the conductance across the interface and this parameter that is proportional to the work of adhesion. Okay, and these experiments and simulations were verified again in this work by, I think it was 𝗲𝗃𝗃𝗃's group in 2013. And again, you see that kind of a relationship, it's evident, it's pretty evident. So apparently, the work of adhesion is proportional to the thermal conductance across the interface. But this is just from empirical observations, right? And more recent simulations have, experiments have shown, for example, with plasmonic nanomaterials, that that relationship is not that straightforward. It's not that simple. And this is in 2016, and more recently in 2019, Patrick Hopkins showed no relationship whatsoever with the transmission of energy across solid-liquid interfaces as a function of the work of adhesion. As you can see, these data points are all over the place. No linear, relationship was observed, and this also matches my modeling efforts, which I'm going to show you now. So this is how we model heat transfer across solid-liquid interfaces, a very traditional non-equilibrium model that resembles an experiment in which we create a temperature gradient across a system by injecting heat, a given amount of energy on one end of the system, rejecting the same amount of the other extreme, waiting for steady state, and then we calculate the temperature discontinuity at the interface such that we can calculate the thermal boundary conductance given in this expression. In addition to this simple calculation, we also perform a more granular calculation by going directly at the interactions between the solid and liquid atoms at the interface. And this calculation right here also allows us to calculate the spectral makeup of heat transfer. So the heat transfer distribution as a function of frequency of the modes going across the interface. And then we can calculate from this granular calculation, this atomic-based atomic scale calculation, we can also calculate the thermal boundary conductance as indicated here. The results that I'm going to show you next are a combination of both. And let's go see them. Okay. All right. First set of results show a kind of messy results that show no trend as we were expecting, right, from previous experiments and simulations. Well, actually, this verified the experiments by Hopkins, but there's no relationship. What we would expect to see is this point over here, more hydrophilic, having higher conductance. That's not what we observe. Those calculations that the calculations that you see here are both using the straightforward calculation of the heat flux and the granular calculation of the heat flux. And as you can see, the results are consistent. Next figure, okay, this is as a function of the contact angle. Next figure, okay, let's take the work of adhesion. Maybe we're missing something in this calculation, right? So same thing, we would expect to see this point over here to show that a more hydrophilic surface transfers more energy. That's not what we are seeing. All right, we just say, okay, let's take a look at another metric. The total interaction energy. Maybe you're thinking, you know, the contact angle is not that physically sound because it's also a function of the granularity of the interface, or the work of adhesion suffers of the same issues. Just look at the pure interaction energy, which is what we have here. Same trends. We would expect to see this point over here. That's not what we observed. And then we wanted to verify maybe the relationship between the work of adhesion and the total interaction energy is not correct. And that was not the case. As you can see in this figure, there is a linear relationship between the interaction on energy, the total change in the internal energy of the system, interfacial energy, and the work of adhesion. So we confirmed that that was not the case. So our interface model is physically sound. The relationship between our interface interaction metrics are physically sound. It's just that the thermal transfer doesn't make sense. But this is not the first time that we observed this. Okay? So we observed it before for silicon carbide interfaces, in which if you plot transmission of energy, the thermal boundary conductance versus the contact angle, you see that it doesn't really follow a universal trend, a universal line, even if you change the metric from the contact angle to the work of adhesion. And it changes as you change the plane in contact with the liquid. My dissertation work also showed the same, but I added an extra level of complexity, another level of robustness, in which I included these two data points that account for the same wettability for a more complex system, of a system coated with graphene that was theoretically, experimentally, and computationally demonstrated had the same wettability. And as you can see, it's a complete breakdown of those predictions. And more recently, we investigated different approaches to model a graphite water interface. So many different interaction potentials derived using empirical methods, wettability, DFT, advanced, novel electronic structure calculations. And again, we see no relationship whatsoever in our calculations. But later on, I'm going to show you later on how we were able to reconcile this. But first, in our granular calculations, and I was saying, we were able to calculate the distribution of modes in terms of frequency. As you can see here, the bulk area, the gray shaded area, is just the bulk availability of modes in alumina. And as soon as we come in contact with water and we passivated this interface, we observe the creation of these new modes by the peak magnitude, the width, the frequency, the range, and everything, we can say that these are optical modes of very low velocity that are going to contribute a little to heat transfer, not that significant. But it was interesting to observe the creation of this, but only at the interface, right, for all the surfaces. And as I'm going to show you next, they really do not contribute a lot to heat transfer. Okay, now we characterize the composition of interfacial heat transfer in out-of-plane and in-plane calculations, and I'm going to show you two interesting cases: alumina, crystalline alumina, and amorphous alumina. The Coulombic interactions have this makeup. As you can see, most of the energy transfer in the crystalline system is out of plane. It's kind of 70-30 relationship of the transmission, and this little bump that you see right here is that contribution from the optical modes that were created at the interface, and as we predicted it, they don't really contribute much, but it was just interesting to see that. Same thing, you can see the little bump over here for the amorphous system, but this is quite interesting. If you look at the lines, now the in-plane modes are contributing the most to energy transfer. I would say a maybe 60-40 relationship. It was completely inverted. Also, for van der Waals forces, we observe the same behavior. You can see here in the crystalline surface, out of plane contributions make the most of the energy transfer, and that relationship was inverted, where in-plane calculation, in-plane modes contributed the most to interfacial heat transfer. How can we explain that? From the interfacial entropy. The interfacial entropy change for the first crystalline surface that we see right here is super small, while for the amorphous system is quite large. And what does that mean? What does that mean in terms of the transmission of energy across the interface? Well, if you take a look at the distribution of liquid molecules at the interface, for that crystalline hydrophobic plane, the change from the bulk to the interface, as indicated in this peak, is quite minimal. So that means the interfacial entropy change is not that significant. For the amorphous interface that I showed you, as you can see, it is kind of broken from the bulk. There is a lot of variations of the interface, a very large peak, and then we have other secondary peaks close to the interface. And that's because of the closeness of the particles close to the interface. So we have more availability of energy carriers. They get closer, they interact in a stronger manner. And as you can see in the green particles over here in this video, they remain closer to the interface, and they are allowed to transfer energy in that direction, in the in-plane direction. While the more hydrophobic one, less granular interface, mostly transfers energy in the out-of-plane direction. By the way, the coloring of this animation, it goes from red to blue, where the blue colors represent more heat transfer and the red ones represent less heat transfer. As we were expecting, most of the energy transfer happens between 2 and 4 angstroms from the interface, and that's where we see the most drastic change in the distribution of water particles at the interface. Again, in these systems, the water molecules are the energy carriers. Okay. Lastly, I'm going to finish this discussion on interfacial transfer using the metrics that were able to explain what was happening. For this highly polar interface, the creation of hydrogen bonds was the most significant mechanism for energy transfer, in which we finally were able to explain what was happening here. As we increase the concentration of hydrogen bonds per area, we also increase the transmission of energy. And as I have been pushing for this idea since 2016, the availability of the energy carriers across the interface help to describe energy transfer. In this case, we don't have, these are not really phonons. The particles transfer the energy, and using this liquid density diffusion calculation, we account for 1, the closeness of the liquid particles to the solid interface, and 2, the concentration of the liquid particles at the solid at the interface And when we average this calculation over time, as it's performed to obtain the energy density, we get those calculations of concentration over time. And as indicated here, the previously calculations reported that made no sense make complete sense by just looking at the distribution of the energy levels. Now, this calculation is not unique. We have, as I said, I've been pushing for this idea since 2016. We observed that for silicon carbide, those previous calculations that I showed you that were crossing each other and were not making a lot of sense. Using the density depletion, they are completely reconciled. We observed the same one for silicon surface coated with graphene, and we observed the same behavior for graphene graphite surfaces modeled using a wide range of modeling approaches. All right, and then now briefly, let me just finish this presentation. Now that we performed this, to summarize again, right? A robust model of the interface, plenty of efforts were dedicated to have a physically sound model of the interface. Then we characterize the affinity between the liquid and the solid, heat transfer, and we finally applied this modeling of, this preliminary data to model boiling in a more realistic system, as indicated here. The model that we are using here is, again, chemically sound, physically sound. We account for van der Waals forces, Coulombic forces, and what we did here is to account for the effect of electrostatic forces in these two models, the Lennard-Jones interface and the Lennard-Jones and Coulombic interface. Lennard-Jones and Coulombic interface accounts for both interactions, has a given wettability, and we modified this interaction potential to have the same wettability, but it's only van der Waals interactions. The calculations and the results were drastically different. As indicated here, the model that only accounts for Lennard-Jones interactions presents a decaying, a liquid film that decays faster, that gets smaller faster than the Lennard-Jones plus Coulombic interface. And also we observe higher rates of evaporation as expected. You see, the fluid film is getting smaller, so it means we have more evaporation as compared to a more physically sound Lennard-Jones plus polarization plus electrostatic interactions model. The reason for that is, it was kind of pretty obvious, but it's significant that it gets ignored in the literature, is that the range of effect of the Coulombic contributions, the electrostatic contributions, goes way beyond the cutoff for the van der Waals forces, and not only affects the wettability that you see, the energy transfer that you see, but it's also going to affect the rate of evaporation that you see in your models, and you need to be very careful with that. Okay, all right, so thanks so much for your time, and the questions that I had here for open discussion, the key aspects from my presentation are, how can we proper model interfaces? I want to push forward this idea that we need to dedicate more efforts towards having a physically sound interface model. Questioning why wettability can be used to assess the affinity between these interfaces. This question right here, I have observed this in my models, but we need experimental verification, and I'm looking for somebody to help me with that. And also with experimental probing of the thermal boundary conductance, probably spectroscopy and X-ray diffraction to look at the interface, its chemistry, and its physical properties. Okay, and with that, I'm done with my presentation, and thank you so much for your attention.